Hi everyone, my name is Senapati Rao and I am a mechanical engineering student at PSG College of Technology. Today, I am excited to share my project where I developed a reduced order model for NACA 0012 airfoil based 3D wing simulation using Altair Twin Activate. So, the problem I wanted to solve, as you may know, aerodynamic analysis of something like 3D wing is incredibly time consuming and expensive. If you want to test multiple conditions, you have to run each simulation one by one. This process is slow and just isn't practical for integration into large system simulations. And the goal of my project, my main goal here was simple: find a way to give this result much faster. I wanted to create a fast, predictive AI model in Altair Twin Activate that could mimic this complex analysis. The final plan was to use this AI model in a simple 1D simulation to get key results like lift, drag, and pitch moment almost instantly. First, the open source dataset collection. To start, I decided to build a proof of concept model. I found a great open source dataset on Kaggle called Deep Layer Wing for the NACA 0012 airfoil. This dataset had everything I needed to get started: angle of attack, Reynolds number, and the resulting coefficient of lift, drag, and pitching moment. So, building the first model. Using this data, I went into Altair's RomAI director. I set the angle of attack and Reynolds number as my inputs and the aerodynamic coefficient as my outputs. For the model itself, I chose a nonlinear neural network with 4 hidden the first model results. The results were fantastic. As you can see, the test loss was incredibly low. The R squared values here were 0.97. Here, for the instant evaluation, the lift coefficient hitting an amazing value of 0.999 with a normalized error all are below 5%. This is the RomAI model deployment in the Altair Twin Active. These are the results of the open source dataset model that I have created. The second approach, creating the custom dataset, the self-constructed dataset collection. With the first model success, I was ready to take it into the next level. This time, I wanted to work with a full 3D wing, so I designed a NACA 0012 wing in NASA OpenVSP software and then used its built-in tool VSPAERO to generate my own dataset. I ran a whole series of simulation, sweeping through Mach numbers from zero point 0.1 to zero point 0.7 with an angle of attack ranging from -4 to 24°, and the solutions are exported as the .csv file. Building the second model, RomAI model using self-constructed dataset. I fed it into my new custom dataset. Then it was back to the RomAI director. I fed the new custom dataset. My inputs were now Mach number and angle of attack, and I was predicting a much wider range of outputs, including different types of drags moments around all three axes. I used a similar neural network setup as before. Second model results. The results were even better. The R square values were nearly perfect. These are the accuracy checks. Instant evaluation. Use the same results as my target. Now, the normalized root mean square error, which has a 6.7 in the coefficient of movement about the z-axis, which is less than 7%, and the remaining values are showing a great normalized RMSE value, which means the RomAI model is a high accuracy model. And the final 1D simulation in Altair Twin Activate. Putting the same model to work, I took my trained model and dropped into the 1D system simulation. Here, the AI model acts as the brain, instantly predicting the aerodynamic parameters. The setup is simple with the simple inputs of Mach number and angle of attack as a saturator ramp. In this example, I have set a constant Mach number of zero point 0.4 and I am changing the angle of attack from -2 to 18 degrees. As just like that, you can see the results pop up in real time. Get instant calculation for lift force, drag force, and lift to drag ratio and all other coefficients. This process takes less than a second. These are the plots generated from the 1D simulation. So in conclusion, I was able to successfully replace a slow complex 3D simulation with a fast and accurate AI model. I created a 1D simulation that gives the result in seconds, making it incredibly cost effective and quick. So opens up amazing possibilities for real-time application like designing the active flight control systems. Thank you.